Hello everyone, today I featured a music video. It's actually Old Town Road. Okay, if you have watched this video, you may have realized that we're already done with all the stress and strain types. So we'll kind of start to review. So we're showing you more methods for stress and strain analysis, like in chapter 8. Okay, we're talking about stress and strain transformation. Those are actually methods for stress and strain analysis. In the rest of this semester, we have 3 chapters left, chapter 8, and then chapter 9, we will talk about pressurized vessels, and chapter 10, combined loadings. Those are 2 small chapters, so we'll only just give methods for applications of the previous learned theories. So chapter 8 will be the last chapter in which we'll have new theories for stress and strain analysis. Okay, so today in this chapter, we will focus on stress transformation, and we will draw stress elements and transform the stresses. And we will also explain why we need to do stress transformation, and introduce the concepts of principal stresses. Okay, this is the chapter 8, stress and strain transformation, and section 1 we will focus on stress transformations. We will start from 2 lead-in examples. Well, in the first example, we showed a T-shaped section that is subjected to an axial force P, internal shear force V, and an internal bending moment M. To determine the normal and shear stresses at a point H, show the stresses on the stress element. And all the dimensions have been given. This T-shaped section can be divided into a flange and a web. So the dimensions of the flange and dimensions of the web have been all given, and also give a d, that is the distance from the top surface to the point H. Okay, so first of all, let me ask you, what equations are you planning to use for the calculations of normal and shear stresses? So the first equation will certainly be sigma equals P over A. Right? We will use this equation to calculate normal stress induced by the axial loading P. Right? So other normal stresses, since we also have a bending moment M, so you will have bending stress that is also a normal stress. Right? So the normal stress induced by the bending moment can be calculated by My over I. Right? Those are the 2 components of the normal stress. Now how about the shear stress? Tau equals V over A. Right? But is this the equation, the correct equation? Recall that we used this equation in earlier chapters to calculate the average shear stress on a section. But here we're asking a shear stress at a certain point, H. Right? So obviously we will not use this equation. We will use the equation we learned from the last chapter, that is VQ over IT. Right? You already got all of the equations we need to use for calculation of normal and shear stresses. So the first step, we will need to determine the section properties. Right? So the area of the T-shaped section will be the sum of the 2 sub-areas, the flange and the web. Right? For the flange, you have 8.1, and the web, you have 10.0.8. You get 16. And for the Y bar and I will skip the steps. I will directly give you the results. Okay, the Y bar is 3.25 inch from the top. And the I can be calculated as 188.3 inch to the 4th. Okay. Then in chapters, steps 2 and 3, we will calculate the 2 components of the normal stress. Okay. Then step 2, we'll calculate sigma 1 induced by the axial loading. So here the equation would be simple, right? Since you just need to use P over A, right? The P is 3,500 over 16. So you get a 219 psi. Look at the direction of the P. So it's tension, right? This is a positive stress, right, in tension. Then how about the second components of the normal stress induced by bending moment? This sigma 2 can be calculated by my over I. What is the value of m? Well, look at here. It is 4,500 pound-feet. So we need to convert it to pound-inch so that we can use inches to calculate the value, right? So here's m is actually 4,500 times 12. Right? Then how about the y? The y measures the distance from the centroid to point H. Right, this is the y. Obviously, the y equals y bar minus the d equals 2. Right, so we got a 3.25 minus 2. Then over I, the I has been determined as 188.3. So we will get a number that is 358 psi. Is this in compression or tension? Positive or negative? So we need to examine the direction of the m. Right? Look at the m. Is the m positive or negative? Obviously, the m here, shown here, that is a positive bending moment, right? Meaning that at any point above the neutral axis going through the centroid, well, your normal stress is negative, right? In compression. So here we need to add a negative sign to this value, since this is in compression. Right? So what is the overall? What is the overall normal stress at the point H? The overall normal stress at the point H can be calculated from sigma 1 plus sigma 2. Right, that is actually 219 minus 358. So you get a negative 139 psi. This is the overall normal stress at the point H. Then in step 4, we can calculate the shear stress. Okay, tau equals VQ over IT. We already know V, I, and T, so we just need to determine the Q, the value of the Q. Right? The Q can be calculated by summing AI DI. Right? So we cut the area at point H, so we get the shadowed area. It's a smaller T shape. We can further divide it into two areas, 1 and 2. Right? For the sub area 1, its A obviously is 1 times 8, and the D value will be from the centroid to the local centroid. Right? So that is y bar minus half of the thickness of area 1. Right? So that is a 3.25, the y bar minus 1 over 2. Plus the area 2. So the area of sub-area 2 will be, as indicated here, you have a thickness that is 1. Right? It's 1 times the thickness of the web. This is 0.8. Right? 1 times 0.8. And what is the D value for this sub-area? It's from the centroid to the local centroid, or what the this distance plus half of the thickness. So this distance showing here is actually the y bar minus 2, right? So that is a y bar minus 2 plus half of the thickness of sub-area 2. That is also 1/2. Okay, so the result of this calculation would be 23.4 cubic inch. Then the tau can be calculated by VQ over IT. The V is 2000 times 23.4 over 188.3 times, what is the thickness? The thickness is here, right? That is the TW, the thickness of the web, or 0.8. Right? So we get the result that is 311 psi. Okay, now we already determined those normal and shear stress components, so then we can draw them on a three-dimensional stress element. Okay, as shown here, we can cut this three-dimensional stress element out from point H, so you get this three-dimensional element. You can see that on the external surface, the H plane actually do not have any shear stress. You have only a shear stress determined on the green colored plane, right? That is 311. Right, this is the 311 we just calculated, and because of the dimension, the direction given here, right, it's upward. Right, so we got a upward 311. To balance it, you will have another component on the negative x coordinates direction. On the negative x plane, you have a downward stress components to balance it. Right. As we explained in the last chapter, the characteristics of a three-dimensional element, stress element, you have another tau component on top in the positive x direction, and its value equals the vertical shear stress. It's also 311. And to balance this one, you will have another component on the bottom pointing negative x direction. Okay. Then since the shear stress on the on the H plane is 0, so we can simplify this three-dimensional element into a two-dimensional case. Okay, we just draw a two-dimensional stress element. This is the plane H. This one has a upward shear stress on the positive x direction, and you have a negative downward shear stress on the negative x plane, right? Then you have a tau on the positive y plane and a tau on the negative x plane, right? Those are the shear stresses, 311 psi, and all of these four components have the same magnitude, right? So then the overall stress, as we calculated here, this tension and compression, the resultant will be a negative 139 psi. So along x direction, we have a normal stress, negative 139 psi. Okay, so this is a two-dimensional stress element at point H. Then let's look at a second lead-in example. And here we analyze a torsional element. Okay, a hollow shaft with an outside diameter of 142 and inside diameter 128 is subjected to a torque and the axial tension load P. Then determine the normal and shear stress at the point H and show them on a stress element. Okay, what is shown here is the hollow shaft, and you can see there's two external forces, P and T. Okay, let's separate them divide them into two drawings. Okay, the first one, in the case 1, this hollow shaft is subjected to a P, right? There's a P in a positive X direction. And the second case is subjected to torsion, right? Just use your right hand rule and look at the direction of the T, right? Use your right hand rule, you will know that it's subjected to a torque T. Use double-headed arrow, right? This is the T. Then you can cut a 3-dimensional element out of point H as shown here. So we will analyze the stress components of this element. So first of all, we can calculate the normal stress. Since here you have only one axial loading, no bending moment, so we have only one component, right? You just need to use this equation, right? Sigma equals P over A. Right here, the A equals pi over 4 d squared minus d squared. Right, that is pi over 4. These two diameters are 142 and 128. Right, it's 142 square minus 128 square. You get 2970 square millimeter. Then the stress can be calculated by P over A, and that is 60 kilonewton over 2970. You get 20.2 MPa. Okay, this is Newton per square millimeter. You get MPa directly. Then the shear force. Here the equation we will need to use will be Tc over J. Right? So we don't know J yet, so we need to calculate the J. Here the J equals pi over 32 d to the 4th minus d to the 4th. Okay, so you will get a result that is 13.6 million mm to the 4th. And the C will be half d, right? That is 71 millimeter. So the shear stress can be calculated by Tc over J. That is, look at the T, the value of a T. The T is 12 kilonewton meter, so we need Newton millimeter, right? So that will be 12 million Newton millimeter. So we get 12 million here times 71 over 13.6 million. Then we got 62.65 MPa. Okay, now we already determined this normal stress and shear stress, so we can draw them on this 3-dimensional stress element. Okay, so first of all, we have a tensile normal stress, well, that is 20.2. And then we have just look at the direction of the torque. Look at the direction of torque. Okay, so this result of this torque T on the green colored surface will be upward. Well, will be upward shear. So this value is 62.65 MPa. Okay, to balance it, you will have another component here. On the top surface, you will have a shear stress with the same magnitude. And to balance it, you will have another component on the bottom. Okay. Again, this purple colored plane H has no shear on it. Right, so we can simplify it into a 2-dimensional case here. This is a plane H. Then on the right hand side, you will have a upward shear. Here, downward shear. On the top, you have a right pointing shear, and on the bottom, left pointing shear. And their magnitudes are the same, 62.65. And along x direction, you have a normal stress that is 20.2 MPa. Okay, here we just get the two-dimensional stress element of point H.